Okay, so now let's get to the part where we install LAMPS and try to implement whatever I've taught you in the or whatever I've discussed in the previous MD basics. Now, let me minimize my screen. All right, the first step is to download and install LAMPS and also build LAMPS. Let's start off with a very simple search. We say just LAMPS and we click on the first link that you get there, which should bring you to this page called, this is the home page of the LAMPS software. Now, here you can see a list of all the different features of LAMPS and also the usage, the widespread usage of LAMPS by different studies. So these are all the covers and so on. So here I mainly want to download LAMPS. So for that, I click on the download link. So once again, let's go a bit slowly here. So for downloading LAMPS, you need to click on this link here at code. All right. Now, you can download the latest version of LAMPS that's shown is here. But for our purposes, which is also to calculate not just the density, but also the diffusion coefficients at a later point, we will be using a special plugin called the OCTP, which is developed by the Engineering Thermodynamics group at TU Delft. And to enable calculations using that plugin, we need a LAMPS version that is compatible with that plugin. And for that, you need to download the older version of LAMPS. So the LAMPS releases regular versions from time to time, and it uploads it or it releases it on its website that as shown here. Now, to download this particular version of LAMPS, you need to go to the page here. So all you have to do is scroll to the bottom of the page and then click on this particular link here. Once you click on the link, it just lists all the previous versions of LAMPS that are developed and that are released. And for our purposes, like I said, for the sake of compatibility, we require the version that's shown here, which is the 6th of June the 22nd of June 2022. And the file is called lamps 2nd June 2022 tar.gz. So it's the extension tells you that it's a zipped file and it contains all the files required to run a LAMPS simulation. So let us click on this. As you can see, as you click it, you will see that you can track the progress of the download. It's a file 163 MB large and it's pretty fast in downloading due to the Wi-Fi here. So I guess it will be the same for you as well. All right, so now the LAMPS is downloaded. Now let us go to the folder where it has been downloaded, right? So I'm already at the folder where where the LAMPS folder has been, or the LAMPS zipped file has been downloaded. So you can see that I'm using a terminal on my Mac OS. So I'm using commands which are suitable for the LAMPS. Now, there are two ways to unzip this file. You can either do it manually. Let me show you. So if I go to downloads, you can see this file. You can either, if you double click this, it automatically gets unzipped. That is one way to do it, right? But if you wish to completely do this on the terminal, then I would use this command. All it's telling is unzip the file, provide some verbal commands, then it's a zipped file, and then you have some other commands to enable the unzipping of this particular tar.gz file. So now if you want to unzip a tar.gz file, this is the extension that you would typically use. So now let's click on this. And once you enter, you see this huge list of files that it generates, or the huge list of files that it generates while unzipping. So if you now do an ls or an ll, it lists now the folder that was previously not there. So this is the folder which has been now unzipped. Now you can go inside this folder and can once again look at the contents. And if you look at the contents, you have different folders here. The folder that we are now interested in is called the source folder, which is the SRC folder. So this is what we'll be looking at right now. And if you want to work on some examples of LAMPS that are also available in the examples folder. But for now, we will just use it as a means to an end and use it to only demonstrate the calculation of densities. Okay, so now to install LAMPS, you need to go to the SRC folder, and the way to do that is you write the cd command, which is used to navigate through or navigate to different folders, and then you say cd src. And now you're already inside the SRC folder, and you can see that the SRC folder contains many different files. And note that the LAMPS is written entirely in C++, and there's also a Python version available. So now if you see, all of the files have been listed here in the in this SRC folder. All right. Now, in order to install this, what you have to do is, like I said, first go to the LAMPS SRC folder, and we need 3 packages here to build LAMPS. And the packages that you require are called kspace. The kspace package is for calculating the electrostatic forces between particles. So this is very, very important. This is an important package. The next package is called rigid. So the rigid package is for rigid molecules. So if I'm simulating um, molecules like CO2 or even hydrogen as a rigid molecule, which we will do so in this particular example, then we need this rigid package. So what we're instructing LAMPS is to basically include rigid, include the K space, which is for the electrostatic forces, and also for the molecule. So when you say make yes molecule, it's going to basically include all of the molecular force fields that are required for running LAMPS. Yeah. So this is for molecular force fields. Yeah. So let's do that. Let's do it one step by step. So let's first say make yes K space. Now, if you're not able to see this, let me increase the size of the terminal, or the size of the font. So let's first say make yes K space. And if this happens successfully, then it'll tell you, it'll give you this message that it's installing the package kspace. Okay, so once this is done, let's move on to the second package, which is make yes rigid. Once again, it tells you that it's installing the package rigid. And finally, let's install the make yes molecule. Once again, it installs all the necessary packages for the molecule. All right. So now you've instructed LAMPS to include all of these packages while building. Now, you can run LAMPS in 2 ways. You can either run it as a serial code, in which case it runs it on a single CPU, or you can run it as an MPI. You can execute it as an MPI, in which case it's going to run it on several different CPUs using the message passing interface or the MPI architecture or infrastructure. So for the case of simplicity, I'm going to assume that we can do all of these calculations on a serial node or on a single CPU. So I'm going to install LAMMPS using this command, make serial. Now, if you wish to do it on make MPI, you will, this is just a simple command. You just need to run this. The only difference occurs when you're running um, the, um, the code or the LAMPS code, uh, which I will show you at a later point in time. But for now, this would suffice for us. So let us say make serial. So now, as you see, it's making all the files required for, like it says here, compiling lamps for machine serial, right? So this is what we want. Now it's showing you a list of all the um, CPP files and also the H files, which are required to run lamps in serial. So this will take some time. And sometimes lamps does show some warning messages to instruct you that certain packages are missing or certain commands are depreciated and so on. So in such cases, you will have to carefully look at it. It could also happen that it has no consequence on the final compiled file. Like you see here, now it's generated many different warning messages, but in our case, I can assure you that this has no effect um, on the final executable. Yeah. So as you can see, this is quite a long process because it has to include all the files required for the installation. All right. So you see that finally it exited without generating any error message, which means that it has finally managed to, as you see here, there are 7 warnings generated um, with regards to these files, but then finally you have a executable. And to really check that you have the executable, what you can do is so this is the file that it has generated, LMP serial. So let us see if you have this file. As you see, um, the entire process has generated an LMP serial file. And this was generated at 11:18 on May 27th. And this is precisely the point that we're interested in. So this is successful now. So we have the file to run the MD codes. All right, so now this should be done now. So you are ready with the installation of LAMMPS. Now let us run the example, the much awaited example where we calculate the or compute the density of hydrogen for one particular mixture. Yeah. So let me go to the folder where we have the input files. So this is the location where we have the script. Okay. Now, so you're in the folder where we have all the input scripts required to run or interface with a LAMMPS software. Now, the most important thing while running a LAMMPS program is the input script. So what you need to describe in the input script is basically how you will initialize the positions of the molecules, how you're going to initialize the velocities, what's the size of the box, what are the force fields that you require to simulate a material or a gas or a liquid, and so on. So these are the main features of an input script, and this is very crucial. So if you define your input scripts in a right way, then the results that you extract can be reliable. All right, so now to give you an idea of how the input scripts look. So here is an example. So this is my input script for calculating the density of hydrogen at a given state point. Now, here in the description, I say CO2, a system containing rigid molecules of CO2 and H2, but that is because I wish to also show you at a later point in time how to simulate a mixture. And like I said, we wish to calculate the diffusion coefficients as well. And for that reason, I've chosen an input script which can also simulate CO2. But then we can also tune, or we can also choose how many of CO2 molecules should be there in the script. So that can be set to 0. So in functionality, we are actually simulating only hydrogen in this particular case. Now, what is important to note is that all the hash symbols, all the text that follows the hash symbol is basically treated as comments and is not executed by the LAMP script. So I've also written the date here for convenience. Now, before you mention anything, the first thing you need to initialize in LAMPS in input script is things like the units. Now, we want the LAMPS to input and accept input and also display output in real units. Now, to understand what these real units are, it's always good to go to the LAMPS documentation. And the LAMPS documentation is quite well written and you have all the information there. So all you have to do is say real units LAMPS, and you end up with this page here called units command LAMPS. So in this, you see that it tells you what's the syntax of this command. It says units and style. And this is exactly what I've done here. Units, and then the style is real. All right. So now if some of the examples are units metal, units LJ. So units LJ is basically for Leonard Jones, and units metal is units that are relevant to a metal, right? Okay, now if you want to look at what exactly you have for unit real, which is what we are using, let me see where it is. Here it is. So now in unit real, we have mass expressed as grams per mole, distance expressed in angstroms, time in femtoseconds, energy in kilocalorie per mole, velocity in angstroms per femtosecond, and so on. So this is roughly the units, or this is the units that we are going to use to represent and also read the output from the LAMPS program. Atom style full. Now, when you say atom style full, once again, let's learn to use the as I said, let's learn to use the documentation of LAMMPS. As soon as you type atom style, it already gives you the web page which contains documentation. Once again, the syntax for the command is atom style, and then there are some arguments that you can optionally provide, right? Now, if I say atom style atomic or atom style molecule, atom style full, I'm sorry, when you say atom style full, it gives you access to all the molecular force fields. That's the reason why you have this, that's the reason why you need to specify all of these commands here. Now, you can also use other types of commands. You can use atom style atomic, in which case you're looking at atomic liquids, solids, metals. If you're looking at DPD, or if you're looking at a coarse grain technique like a DPD, then you say atomic rho plus reactive DPD and so on. So you have all of these different options which you can use here. For our case, we are mainly interested in simulating realistic molecular force fields, and for which reason we are going to use the full attribute or the full style. Next, the most important thing here is to also specify what kind of boundaries you have in your simulation, or the boundary conditions in your simulations. And I already discussed with you that we usually use periodic boundary conditions. I mean, it's not that you cannot use other boundary conditions, but for our cases right now, it's the periodic boundary conditions should suffice. All right, next you have something called as the pair style command. In the pair style command, you instruct LAMMPS to see how the molecules actually interact with each other. So here we say LJ cut Coulomb long, and then the cutoff radius, or the interaction cutoff for the molecules. So once again, you can type this here. You can see pair style LAMMPS. And here you see that, as I said, now we are going to simulate hydrogen in a case where we are also interested in the electrostatics, not, as I said, in the total potential energy. You're not just interested in the Leonard-Jones potential, but you're also interested in the electrostatic interactions between molecules, because in real life, or in reality, molecules actually have partial charges, which, as a reason of which, they interact with, they have electrostatic forces acting between them and on them. So that's the reason I've also chosen Coulomb long in addition to the Leonard-Jones with the cutoff. And when I say Coulomb long, it means that it's going to calculate Coulombic forces, long range Coulombic forces, and the cutoff for the Leonard-Jones and the Coulomb Coulombic interactions is 10 angstroms. So here 10 means 10 angstroms, because here you see that the pair style, you first choose the style and then the arguments. All right. Next, we have to specify also how the molecules between two different atoms or between two different species will interact with each other. And there you say pair modify, mix, arithmetic. So which means that we use arithmetic mixing rules between any two species. So what I mean by this is, let us say that you have two different molecules. You have, say, hydrogen and carbon dioxide, which we want to use later on. Then what it basically tells you is that you're going to use a mixing rule that is arithmetic in nature. So you see here, I can search for arithmetic. So if you have an arithmetic mixing rule, then what it tells you is that the energy of interaction Ij, so you have I as H2 and J as CO2. Then if you have a mixture, when you have two molecules of H2 and CO2 interacting, then the Leonard-Jones epsilon that you will use is a square root of the individual epsilon, and product of the square root of the product of the individual epsilon I and epsilon j. Similarly, the sigma ij that you will use is half of sigma I, half of the sum of sigma I and sigma j. So these are basically called combining rules, which are very essential when you're simulating mixtures, because you need to specify how the mixtures need to interact with each other. All right. What you also need to specify is something called as tail, the tail interactions. So the tail corrections. So if you remember, I specified that we always need to take care of something called as the tail corrections, which are the long range corrections in both the energy and pressure. And that is precisely what is being signaled here to LAMMPS. So it's telling that if you have a cutoff of 10 angstroms, and if your box is bigger than 10 angstroms, then you need to somehow calculate all of the interactions beyond 10 angstroms. Now, it is very important to note here that if your cutoff radius is 10 angstroms, your box has to be at least more than 20 angstroms. So your box cannot be smaller than 20 angstroms, because if that is the case, then a molecule will start to interact with its own self, and hence, this is according to the minimum image convention, and hence the body really has to, or the box really has to be more than 20 angstroms. All right. So in this command, we're basically saying that you need to take care of tail corrections. Now, bond style, because I said that hydrogen in our case is a rigid molecule, so it has 3 centers. So you need to say what kind of a bond is between these particles, so to say, which build up hydrogen, or the atoms which build up hydrogen, and we say that is harmonic. So there are many different types, but here in this case, we just choose it as harmonic. Once again, if you're interested to know more details about this, you can just enter, or you can just look at the library or the documentation of LAMMPS. Similarly, angle style is harmonic, but here it's really not required to specify these, as we are using something called as a rigid body convention, where there is no where there are no oscillations in the bond lengths or the fluctuations in the bond angles, because we are setting this exactly as a rigid body, which means that it should move as a rigid unit as it is being simulated. All right, so these are some things that we mentioned to LAMMPS, which are applied throughout the simulation. Now, we also have something called as user-defined constants, and user-defined variables. And these variables I've listed here. So this is basically saying something like A is equal to 10, B is equal to 20, and so on, which we might use at a later point in time. Now, in LAMMPS, I prefer to say that my temperature for the simulation is 323.15 Kelvin. The pressure here is the pressure in atmospheres, because remember that our units are in real units. So then the pressure is 493.462 atmospheres, which is basically 50 megapascals. Then the variable is a random number, which I use for generating the velocities and so on. So that is 77977. That's a random number. So now I say how many molecules of CO2 I want. Since we are only interested in hydrogen, I put this to 0. Now I've chosen a very small number of molecules, which is 75. This is just to show you that uh, this is just to show how the LAMMPS input script works and how you can run it quickly. Now, the only message of warning here is that when you're choosing very low number of molecules, be aware that these molecules can, can be in a very small box, because your pressure is high and the number of molecules are low, which means that your box can be quite tiny. If the box is tiny, you always have to then check if the box has the cutoff or the box length is more than twice the cutoff. So in this case, make sure that make sure that the box length is more than 20 angstroms. Okay. Then I have several other parameters which I've defined here, which I will explain it to you on the go. But for now, I think this would be sufficient. Okay, so the next important step is to initialize. Like I said, the beginning of any molecular simulation requires you to first initialize the particles or the molecules inside a box. So you can always picture this particular image in your mind, and this is what you need to generate. Now, I've written a command here which says to LAMMPS that you allocate a region called REG. This is the name of the region, and it's a block, and the limits of the block are between 0 and box length in the X direction, between 0 and box length in the Y direction, and between 0 and box length in the Z direction in the units of the box. All right. So this is once again a typical LAMMPS command in which it helps you to first create a region in which you want to do something. And here I say that I wanted to allocate a region which is of the size box length, box length, box length, which is very suggestive that it's the size of the box. And here I've set the box length to 50, which means that this should be roughly, or this should be 50 angstroms, because all of the units, remember, are in the units of, are in the real units, and in the real units, all lengths are in angstrom. All right. Now, okay. Now, once you've created the region, you have to create the box, and you have to say what are the constituents of the box. So first, you're going to say that there are 4 different types of molecules, or the four different types of atoms in the box. And because I'm dealing with both CO2 and H2, now I have 4 different types of atoms in the box. So C is 1, that is carbon, oxygen, hydrogen, and the dummy atom related to hydrogen, which I will come to at a later point when I'm defining hydrogen. So these are the 4 different atoms of the box. Then I've also specified the region that I've initialized. I've also told what kind of bonds are there inside the box, what are the different types of angles. Now for bonds, there are only 2 types of bonds, one between carbon dioxide, one between carbon and oxygen. That's one type of bond. The number of bonds of this are 2 because you have 2 carbon-oxygen bonds for CO2. And similarly, you have 2 bonds for hydrogen and the dummy atom for the hydrogen. So there are basically 2 bonds for each of these. But the 2 bonds each for each of these, but the bond type is just 2. Similarly, the angle is also 2 types because you have one angle between carbon dioxide, between the oxygen, carbon and oxygen, and between hydrogen, dummy atom and hydrogen. Yeah. Now these extra commands instruct LAMMPS to ignore the interactions between the atoms, which is usually used for speeding up the simulations. Now, I have to instruct LAMMPS what are the different molecules that are there in the system. So firstly, let me show you what I have in co2.txt. So in the co2.txt, I have something called as the, I'm using something called as the rigid Trapi model. So it tells you how many atoms there are, how many bonds there are, how many angles there are. So there's only one type of angle. There are 2 bonds, but it's only a single type. And then I also provide the coordinates of these bonds. So I have one that is placed exactly at the origin, and then the bond length of carbon and oxygen is minus or 1.16 angstroms. All right. Similarly, I also say which types. So carbon is the first, is of type 1, oxygen is type 2, and then these are the partial charges. So carbon contains a positive charge of 0.7. So you have to see which units there are here, because as I said, the units are very important in lamps. So for the real, you can see that the charge is the multiple of an electron charge. So when you say 0.7, it's 0.7 of an electron charge, and oxygen is minus 0.35. And you also specify the bonds. So when you say bonds 1, 1, and 2, what it tells you is that there's a bond. The first bond is between 1 and 1, or the first bond is of type 1, which is between 1 and 2. As you know, 1 here is carbon and 2 is oxygen. So the angle is between carbon and oxygen. There's a second bond, which is also of the same type, which is it's given as 1, and it's between carbon and oxygen. So this is the this is the atom number which uses these bonds. So you have now specified the bonds. And then there's an angle. So there is one angle, and the angle is of only one type, and that is between 2, 1, and 3. So 2 is oxygen, 2 is oxygen, 1 is carbon, and 3 again is oxygen. So that's the angle that you're specifying. And these special bonds and special bond counts basically tell you how to neglect the interactions between CO2 or H2. Now, that was for CO2. Now let's do this for hydrogen as well. Once again, hydrogen is simulated as a Marx and Neelabah model. So you know that hydrogen contains two atoms. And here in the Marx and Neelabah model, you once again have three atoms, you have two bonds and one angle. It's exactly similar to CO2. Once again, the coordinates of these are specified. So the bond length is 0.37 angstroms. And then the important thing to notice here is that there's a dummy atom that's sitting at the center of the hydrogen atom, or the hydrogen molecule, or the hydrogen rigid rotor. And that is what you have to consider here. And that's the type here that we said. That's one type. And then you have the two hydrogen atoms. Now, note that the dummy atom is of type, it has a partial charge of minus 0.936 electrons, and the other two have a 0.468. Now, what's important to notice is that overall, the charge neutrality is maintained, because if you sum up all the three, then you have a zero charge. Similarly, bonds. So you have you have two bonds, each of them are of the same type. And the first bond is between 1 and 2, that is between the dummy and hydrogen. And the second one is as well between dummy and hydrogen, which is 1 and 3. Finally, the angles. Now you have angles that is between 2, 1, and 3. This is exactly the same as what we had for CO2. So we have hydrogen, the dummy atom, and then hydrogen. So that's the angle between the three atoms. All right, and the special bonds and special bond counts basically instruct LAMMPS to ignore all interactions, all calculations for speeding up purposes between the individual atoms within a molecule. All right, now what's important to note is that we've specified now the region of the box in which we want to populate the molecules. We've also told the LAMMPS about the region, about the number of types of molecules or the number of types of atoms that we are going to initialize. the types of bonds that the box should be aware of, the number of angles that the box should be aware of, and so on. And now all of that is now known to LAMMPS, and we've also feeded LAMMPS which of the molecules are to be expected. Now, to create these atoms, we explicitly tell LAMMPS that you create atoms, and the first number that you put here is the addition that is added to the CO2.txt to the types of molecule to the types of elements in CO2.txt. So let me explicitly say what let me explicitly explain what I'm trying to say. So you have create atoms 0, which means that it is going to add 0 to each of these types. So if you have carbon, oxygen, carbon and oxygen of type 1, 2, and 2, then overall in the final simulation, the type of carbon and oxygen will be 1, 2. Now, here in the second case, you say create atoms 2, which means that it's going to add the number 2 to the type. So the dummy will no longer be 1. It'll be 1 plus 2 in the final simulation, and it'll be 2 plus 2 for hydrogen. So thus you have 4 types, which is 1, 2 for carbon and oxygen, 3 and 4 for the dummy atom and hydrogen. So this basically tells you what should be the added number to the type that's already specified within hydrogen between each individual molecule files. Now, how do we want to create the atoms? Here, I'm explicitly instructing LAMMPS that the creation or the atoms or the molecules should be placed inside the box randomly. I don't want it to choose a specific lattice, for example, like a cubic lattice or a face-centered lattice, which is also adopted in many of the simulations. But I'm asking it to do it in a random way. So here I say, place it randomly inside the box. And I also say how many molecules of CO2 should be there. And since I specified here that n mole CO2 is 0, then it's not going to place any of the CO2 molecules here. And now you can place molecules randomly in any possible way. And for deciding the randomness, you have a random number generator, which I've specified here at the beginning of the script, which is 77977. And so every time you change a random number generator, it's going to generate a new configuration of these molecule positions. And it's going to say that please put it inside a region, which I've defined here, REG. And then it's going to say the molecules, please add the molecule CO2 mol. And then 343 is once again a random number that I've given here. And then here, what it's telling you is that please place it at an overlap of 1.5 or a greater than 1.5, and place it such that no two molecules are within a distance of 1.5 angstroms. Now, it can happen that if your box is very small, and if you're trying to pack many molecules together, then sometimes this criteria is not met. So for example, if I said the overlap should be greater than, say, 20 or 40, then what you're telling LAMMPS is that when you place any two molecules, they should not be close to each other. They should not be within 40 angstroms of each other, which is usually not a difficult case if you're simulating gas, but if you're simulating a liquid where the density is high, then this will be a hard condition to satisfy. In such a case, you can specify how many tries, how many attempts the LAMMPS simulation is allowed before it fails or before it gives up and says it cannot initialize anymore. So in this case, I've given a good number of 10,000. So it's going to try 10,000 times to place all of these molecules such that they do not overlap within 1.5 angstroms. And yeah, if it does not succeed within this within these many tries, then it shows an error message that it shows a warning message that it could not initialize all of the molecules. So please be very careful here, because it can happen that if you intended to specify 100 molecules of CO2, of course not in this case, but if you wanted to specify 100 molecules of CO2 in a very dense phase, but it could only end up putting in together, say, roughly 30 or 40 based on the conditions you've chosen. So kindly check this in the simulation script. Similarly, we do the same thing for hydrogen. And in fact, we have 75 molecules of hydrogen here, and we use the exact same procedure. So once you have initialized the box, now you have initialized the positions of the molecules inside the box. I'm also specifying all the force field parameters. So force field parameters are basically the parameters which you tell LAMMPS that it should use while calculating the Lennard-Jones parameters or any other force fields that you're using. So for example, let us pick CO2. So these are the Lennard-Jones parameters for CO2. And what it is telling is that pair coefficient is the keyword that you have to use here. And pair coefficient 1, 1 means that you pick type 1 and pick type 1. So the interaction between type 1 and type 1, which is carbon and carbon, is given by this particular epsilon and this sigma. All right. So you can also have a look at the pair coefficient command on the website of LAMMPS. So you can say pair coef. So as you see, pair coef tells you I, j and the args. I, j is the numeric atom types, and then arguments are for one or more pairs of atom types. So in this case, you can say what the exact specification is. Let me see where. So here it depends on which type of a force field you're using. So therefore, so let me exactly look for, since we're using the LJ. So in this case, the coefficients are mainly to specify the epsilon and sigma. So this is also for the epsilon and sigma for the for the oxygen in the carbon dioxide. Similarly, for hydrogen, we say that 3 and 3, which is the dummy atom, interacts with another dummy atom with a sigma with an epsilon that is 0.073, and then a sigma given by 2.958. Now, the important part of the Marx-Nielaba model is that the interaction between the hydrogen itself. So the hydrogen is only used for the electrostatic interactions. So interaction of hydrogen with any other molecule is just zero, because it's completely all of the Lennard-Jones interactions are only through the dummy atom here. Now, there are here the molecules are not flexible. So strictly these are not required, because these molecules, what's important to note is that you need to specify what is the bond length, and the bond length is already specified, which is 1.16. So you can see how the bond coef is defined for the case of, So when you say bond coef, you say what the numeric bond type is, and then you specify the arguments for the bond types. And using this, we have now said what should be the angle of the bond for CO2, which is 1.16 angstroms. You can also see this in the CO2.txt file where we specified that the bond length is roughly 1.16. But note that here it is important to mention this because what you provide in the initial CO2.txt file is just the coordinates, but it's not really the property of that molecule. But here for the bond coef, you actually specify it as a property. Also note that the angle is 180, which means that it's a planar molecule and you have one single rigid rotor. Similarly, for hydrogen, you have a bond length of 0.37. This was also something that you saw in the coordinate file that I specified the coordinate to be already equal to the bond length, and then the angle is 180 degrees. All right. Now you specify the masses. Remember that all the masses are specified in units of grams per mole. So if you refer back again to the units of, if you refer to the units of the real units inside LAMMPS, then you see that mass is expressed in terms of grams per mole. And for carbon, you know that the mass is 12.0107, 15.99994, and so on. And similarly for hydrogen, it's 1.008. Yes, another important thing that I would wish to say is that if you wish to know the force field for TRAPE, then you need to go to the website for the TRAPE. These are called the TRAPE force fields, which are basically force fields that are developed for various molecules. And one of them is for CO2. So here you can just type CO2. And you can say get parameters. So it tells you that there are two types of potentials. One is the Lennard-Jones potential, which we already went through. And the second is the electrostatic potential. Now for the, and these are the non-bonded interactions. Yeah, when I say non-bonded interactions, these are not the interactions that are coming out of the bonds and so on. And for each of these, you see what is the parameters. So you see for carbon it's 0.7, for oxygen it's minus 0.35. These are the partial charges. The sigma is 2.8, and the sigma for oxygen is 3.05 and so on. And similarly for carbon, the epsilon is 27, then for oxygen is 79 and 79. What is important to note is that these are in units of epsilon per kb, but in LAMMPS, you need to express all of these units in kilocalories per mole because we're using the real units, right? So this is a simple calculation that you can work it out yourself, and you can convert these data, or you can convert these values in epsilon over kb to kilocalories per mole. And what is important to note here is that this specific model is rigid and therefore has no intramolecular interactions. So this is for TRAPE-CO2. Similarly, similarly for hydrogen, for the Marx and Neelabah field, you can refer to many of the other papers that have been standardly used in the field. So for example, the paper by Rahbari, Ahmad Reza, so you can choose one of these papers to actually read all the information about the different force fields. So if you go to the supporting information of these papers, then you have all the force fields for the different, yes, as you can see, the force field for the hydrogen is listed in this particular paper. Okay, so now we know we have set all the masses, and an important point to note here is for the dummy site, we just want to make sure that it has a very small mass, very small mass, so that it doesn't affect the dynamics of the entire molecule. Strictly speaking, the total mass of the hydrogen should be 2.016 grams per mole. So the mass here should be 1.008 or minus a very small value, minus 1 e minus 10, right? Into 0.5. So what I'm trying to say here is that you need to ensure that the total mass of the molecule is 2.016. So if you're assigning 1 e minus 10 grams per mole to the dummy site, then you might as well remove this mass from the other two molecules so as to give you a total mass of 2.016. But this is almost inconsequential because these numbers are quite small. It hardly has any difference. Okay, so now we have specified the masses, and the charges have already been specified previously in the file itself. So strictly speaking, these are only for specifying the charges, and that is done now. Now for the MD settings, now if you remember me telling that the MD simulations have to be performed um, with integrating, you have to integrate the equations of motion. So for integrating the equations of motion, we went across Verlet. So when you say run style Verlet, then you instruct LAMMPS to say that all of the simulations must be integrated with, or all of the Newton's equation of motion must be integrated with the Verlet equation or the Verlet technique. All right. Another key point here is called the neighbor list. Now, what happens in the neighbor list is whenever you have a molecule, let me perhaps show this on. All right. So here is a file, and here is a list of people. Here is a list of molecules that are next to each other. Now, you need to keep track of the neighbors of each of these atoms or molecules. And if you need to keep track of these molecules, then you need to have a neighbor list for each of these molecules for computational efficiency, because you cannot do it in a brute force way where you loop over all the neighbors at every point in time. This makes the simulation very slow. And thus you need to have some kind of a neighbor list for each of these particles. And that's the specification for the neighbor list here. So you specify what should be the size of the neighbor. So your LAMMP simulation already has a preconceived or a pre-built neighbor list, which is within the interaction cutoff. And you specify this additional 3.0 angstroms on top of the cutoff, which is 10 angstroms, as a way to account for more neighbors, so that if a molecule moves very fast, then it also um, escapes the interaction, and you might have inconsistent or inaccurate results. Now, if you want to read more about this, then you can read this on the LAMMPS website. And this is also, by the way, available in um, Frankel's textbook. And finally, in the neighbor modify, all you're trying to say is that update the neighbor list every time step, and do not do any delays in this. And so this basically tells the LAMP software to build the neighbor list every time step. All right, so now we have specified all the initializations, all of it is done. Now we can go to running the NPT simulations, right? Because we're interested in densities. And if you're interested in densities, we need to know what is the correct volume, what is the correct volume for a given pressure and temperature. Once we know the correct volume, then you know that the mass over the volume should give you the density of the simulation, or the density at the state point that you're interested in. Now, kindly notice that I've not provided any velocities for any of the molecules, and by default, these molecules will have a zero velocity, but in practice, you can provide any velocity you wish. Uh, like I said, you can sample it from the Maxwell-Boltzmann distribution and so on. All right. For now, I've not initialized it, but I see later on I've also done it. So fine. Okay, now for finding densities, you need to tell LAMMPS that it has to perform something called as an NPT simulation. And the way to do that is to say uh, rigid NPT. Now, standard in a typical way, you would just say fix an ID that is defined by me, and then you say all, and then you say NPT. But in this case, since I'm simulating rigid molecules, there are different ways in which to integrate the equations of motion for rigid bodies and so on. And then hence you have to explicitly inform LAMMPS or instruct LAMMPS to um, do a NPT simulation using rigid bodies. So for this, you say fix and the ID is, I call it as my rigid NPT. All is for all the molecules, and then rigid NPT is the keyword here. And this is the molecule keyword that is also supposed to be there. And now you have to tell something about the temperature. You need to specify what is the temperature that you wish to equilibrate to. So that's given by this temperature here. And to keep the temperature constant, there is something called as a thermostat. And to keep the pressure constant, you need something called as a barostat. So to keep the temperature constant, a thermostat works by rescaling the velocities of the particles every few seconds or every few time steps, and you're specifying how frequently you should do that. And similarly for pressure, you're specifying how many times it should rescale the box size so as to obtain the desired target pressure. And you also specify the frequency at which you do this. So the details of this are given in the LAMMPS documentation, but this is more or less the basic idea. And the key thing notice here is the ISO. So ISO means that you're scaling all the dimensions of the box equally. So you're not changing or that you're changing X, Y, and Z in equal amounts. So the box is always cubic in that sense, or you're scaling the box in the same sense. All right. Now, you also need then to specify how you want to print the output. So you have specified all of the things. Now, you need to somehow monitor the output of the simulation. So to monitor the output, I plan to print the potential energy, the kinetic energy, the total energy, as we've discussed before, and the pressure. Now for thermostyle, this is the command that you use to specify how frequently or what are the things that you want to output onto the output file. So thermostyle custom, and these are the parameters that I'm interested in. All right, now you can say what is the frequency at which you should see this on the screen. So NF is something that I've specified as a variable here. So you can see that NF is 50,000. So I'm asking the file to output output these parameters or output these parameters or thermodynamic properties every 50,000 steps, but I can change it to 1,000 steps. And that's what it's going to do. So it's going to print all these properties, which are step, PE, KE, E total, and press. And these are all keywords in LAMMPS. So PE is potential energy, KE is kinetic energy, E total is total energy. All right. Now, let us to run this code. We are almost there. Now we have specified all the things that we need to, and now we're going to run the NPT simulation. So like I said, we need to specify the velocities. We can always set it to 0, but it's also nice to just set the velocities to a Maxwell-Boltzmann distribution. So here I say velocity all create temperature. So what it does is it's going to assign velocities to these molecules such that the net velocity that you get or the net temperature that you get aligns with the temperature. So, and the way to convert the kinetic energy to temperature was already discussed, where we said how the kinetic energy actually can be converted to um, temperature using this particular expression here. All right. Now we're all done. Now we have to specify something called as a time step. So to integrate the equations of motion, what you need essentially is, let us see where we have the integrated equations of motion. Here it is. So you need this dt here, which is the time step for the integration of equation of motion. And the point is that this is a very important choice that the user makes. Now, the time step is usually set by the frequency of oscillations of the bonds in the molecules. So if the frequency is, you want the time step to be small enough to resolve all the uh, oscillations and so on, and you don't want it to be too small because then your simulations are going to be too slow, but you don't want it to be too large as well because then you might have to then your simulations might start to accrue energy or lose energy and show artifacts. So choosing a time step is very, very important. And usually for rigid body dynamics, or usually for molecules having rigid bodies and lamps, the safest choice is to go for a time step of 0.25 or a 0.5 femtoseconds. So in view of that choice, we have chosen a time step of 0.5 femtoseconds. Okay, so now I've started my simulation, or sorry. Now I've started to instruct lamps to start with a time step as low as 0.001 femtoseconds. And I do that, and I run that simulation for using that time step for these many steps. So if you want to see what is NINPT pre, so that's roughly around 1,000 steps. So these are usually called pre-initialization steps. So the reason why I'm doing this is because I've chosen the placement of molecules to be in a random configuration. And what can sometimes happen is that you end up with a bad configuration and there could be overlaps or there could be high energy configurations, which can ultimately lead to your system getting unstable and your simulation crashing. So for that reason, you need to somehow release or you need to equilibrate the system in a nice way so that it approaches a stable equilibrium state. And for that reason, I do several pre-initialization steps. So this is for 1,000 steps. Then I increase the time step by 1 order of magnitude. Then again, perform the simulation for 1,000 steps. I increase by another order of magnitude again, and then do it for 1,000 steps and so on until I reach a time step of 0.5 femtoseconds, in which I do some pre-initialization. And once the initialization is done, I run it for some more time. And in this step, it's called the initialization. Note that these are not strict boundaries. These are something that I've chosen for my simulations. And I've seen that this helps me get stable positions and configurations, which give me then accurate values for the thermodynamic properties that I'm interested in. So doing these steps are quite important, but feel free to play around with these numbers so that you know which sequence of numbers or which values of numbers works best. All right, so now I do the initialization um, based on this using this steps. And finally, once the initialization step is done, I do something called as the production step, which is basically to run the simulation for a large number of time steps. That's what it is. As you can see, I'm running it for 25,000 time steps. So since each time step is around 0.5 femtoseconds, so then this means that this should be roughly around, yeah, 12.5 picoseconds. Yeah, so this is a very small number. So I'm running these simulations just to show that it all works. And then this is this is the time step that I'm running for. Sorry, this is the duration that I'm running for. And finally, I'll generate a restart file so that you can start off from the simulation from the point where you left. And what is important to note is that while I'm running the production step, I'm trying to then monitor the temperature, the density, the pressure, the volume, and so on, right? And I'm also logging all of these into the file. Um, and I use something called as the av time, fix av time. And what the fix av time basically tells you is that you can average these quantities at several steps, from several steps, and then output it to the screen at a different step. So to give you a brief and a quick explanation, so here I'm using these many samples. So nsamp2 is basically 1 into 10,000 because it's a multiplication of n frequency and nsamp1. So I have 10,000 samples that I choose to output to the screen, and then that is what you finally observe. So I'm collecting 10,000 samples at a frequency of 1. So I'm collecting the temperature, the density, the pressure, and the volume at every time step for 10,000 time steps. I average them together and then I output it to the screen. And that you can find it in this file called thermonpt.out. All right, so this was it. So this is all the instructions to run the code. Now let us actually run the code. Now to run the code, you need this script called run. Sorry for this annoying Yep. Okay. So this is what you require. Now you need to specify where the executor file is or the executable is. As I told you, we are using the LAMMPS serial code, and the LAMMPS serial code is available in the downloads folder where this is where I downloaded it. You can download it anywhere you wish, and then you can link it to the executable. Then I have to specify the input file. The input file is npt.in. So this is the file that we just now discussed. And then finally, we have the simprog.log, which is the log file, which I want LAMMPS to put all of the data into, or all of the simulation progress into. You can make it even simpler. You can just say sim.log. All right. And this is the final command that you need to use to run LAMMPS. So you say, if you substitute all of these together, it basically means LMP serial minus I in is npt.in, npt.in minus L log is just sim.log minus variable outdir, and then outdir is just this variable that I used in the npt.in. So you can see that I've specified somewhere that all of the file location should be in outdir, and this is how I specify that. All right. Now we can now run this. That was just to show you how the line will be read by the bash script. Now we say run, and I just say npt.out. and then I put it in the background. So now it's running in the background. You can make sure that it's actually working, and you see that there is the LMP serial here that's working here. Yeah. Okay. So you can also see npt.out. There's nothing in npt.out now for now, but you can see what's happening in simprog.log. It's already started to read all of these files. Now you can see it created an orthogonal box between 0, 50, 50, and so on. It read the template file for hydrogen. It read the template file for carbon dioxide. It even initialized 225 atoms, which is basically 75 molecules. So 75 times 3 is 225. Then it also loaded all the force fields and so on. And finally, you see that there are 75 rigid bodies with 225 atoms. All right, so now it's doing all the calculations. So you can also have a look at the thermo.npt and the thermo.npt.out. So you see that now you have um, the temperature, which is 332.758 Kelvin, and then you have 328.217 Kelvin. So this is the average temperature averaged over 10,000 steps. So it is averaged over 10,000 steps and printed at 10,000 step. This is the density. So this is once again calculated from the masses and the box volume in the NPT ensemble. And this is the average density that you get here. As you see, this is in grams per centimeter cube. So in order to convert this into kilograms per meter cube, you need to multiply this by 1,000, which gives you roughly 37.6 kilograms per meter cube. And the next is the pressure. And once again, the pressure is in units of atmospheres. What is important for you to notice is that it's quite far away from what we set. So if you go to npt.in, our target pressure was 493.462, but now we see that the target pressure here is 748.587 as the first step. But in the second instance, you see that it's already getting better. It's close to 506.696. So it's getting way better. And finally, this is the box volume. This is in terms of angstrom cube. So thermo npt.out. Yeah, so sorry, that was a previous file that I already had, but you're getting close there. So what's important to notice here is that this value, that is 0.028936, that's basically 28.936 kilograms per meter cube. We can also have a look at how well this compares against traditional thermodynamic databases such as RefProp. So if you look at the Excel file that's already available to you, so you can see that at 50 megapascals, 323.15 Kelvin for completely hydrogen mixtures, your RefProp comes out to roughly something like 28.9. So this column here that you see, column G, is from RefProp, and that's that we see is something that's very close to what we have right now. So 50. So that's around 28.9. And the value that we have now is also close to 28.9. So this is extremely close. And this is considering several things. So we have not even equilibrated completely. So it could be that it's not close enough, or it might not be the exact value that we are looking for. But given that we are just using 75 molecules, given that it's a very small system, and given that we have not run it for long enough, these results already show a lot of promise. So this is definitely very close to what has to be. This is very close to the results that we were expecting. Now, if you want to further extend the simulation, you can, yes. So now you see that, sorry, you can see that the simulation ran for 3 minutes and 23 seconds. So that was a very short simulation, but the values that you obtained for the densities were already quite uh, close to what RefProp predicts, which is 28.936. So this is very promising. So if you wish to run this for a longer time and check if the results actually converge quite closely, then please do so. And you can also change the script to add in new materials. So if you wish to add a new component, say for example, methane. So all you have to do is then say pair coef. So firstly, you have to define the methane molecule. So if you want to define the methane molecule, you have to add a description here, right? And for finding methane, methane is usually well defined using the Trappe force field. So you can say methane. So methane is already quite well parameterized. So here you already have parameterization for methane. So this you can already add. So these are the Leonard-Jones parameters for methane. So you can already add this into the code here, and you can replace CO2 with methane. And all you have to do is change a few pieces of the code here. Perhaps if you're adding methane as another component, I mean, if you're thinking of doing it as a ternary mixture, then you can probably add another line for methane. So this you can choose which type, but then you have to convert the epsilon by kb from Kelvin to kilocalories per mole, and then the sigma as 3.73. So this will be 3.73. And that's it. So you're good to go. And here, important to note that methane is a one single molecule. It is not a branched molecule. It does not have a structure, but it's one spherical molecule. So then you might have to think a bit about how you will integrate this into the code. But in a sense, all you have to do is change a few parameters here, and you will be able to simulate methane or mixtures of methane and hydrogen. So with this, I hope to have at least introduced you as or shown you to a molecular simulation to generate data, thermodynamic data for underground hydrogen storage. As a first start, we looked at how to compute the density for hydrogen at one single standard thermodynamic state point. And I hope this will then help you to build on the code, build on this input script, and probably generate more thermodynamic data. So in the next session, I will instruct you how to calculate Fick diffusivities, which are useful for quantifying many underground hydrogen storage mixtures. Basically, the mixing of these mixtures. So thank you for your time, and see you in the next